Sorry I can't be there again. Trying to get better so I can hopefully be there tomorrow with you. This unit on tangents, it's not that bad. We just have to remember how to use Pythagorean's theorem. A tangent in our definitions is a line or a ray that touches a circle at one point on the exterior. So the tangent for this example is line TX or line XT. So let's make sure that we note that with arrows. The point of tangency is just a point, so we use a capital letter. You don't need any other symbols. Points on the interior, they can't be on the edge, so the points of interior for this example is point P and point I. And then points in the exterior, it can't be point T because it's touching the circle, so the only point in the exterior for this example is point X. Alright, to start these examples off with, I cannot stress to you enough the theorem that's noted above example 2 that talks about if a line is tangent to a circle, then it is perpendicular to the radius drawn. So if you recall in my notes, I always start off with circles taken a red, and that's up to you. But I go and I identify all the radii in the circle. So all the reds for this example have a length of 5, which is the radius. Based on the theorem, if the line is tangent to the circle and the radii is there, then we have a right angle. And if we have a right angle in a triangle, then we have a right triangle. And Pythagorean theorem says if you have 2 of the 3 side lengths, then you can use his theorem to find the other side. So I'm going to mark a 5 here because that's the distance for the red. Remember how Mrs. Clements always draws an arrow through the right angle to face the hypotenuse. So for this example, we need to find the length of the entire hypotenuse. So I'm going to do the square root of 5 squared plus 12 squared in the calculator. And that's going to give me a length of 13. Now that's not the answer to the problem. It's saying that from here to here, the distance of CA is 13. Our goal is to find the length of X. So if the entire length of AC is 13 and the radius is 5, then the distance of X is 8. Again, Pythagorean's theorem is what we're going to use to get through this unit. Alright, looking at example 3, it says refer to circle C with tangent AB, and it tells us if the length of DE is 16. So what I'm going to do, instead of starting off with that, I'm going to mark all my radii. So from here to here is a radius, CE is a radius, and AC is a radius. I don't know if I need it, but I just want to make sure I'm marking it so I know they all have the same measurement. It says if the length of DE is 16 and the length of EB is 9, then we need to find the length of AB. Well, since I had marked my radius to get this started, then I know that the distance from C to E is 8. That means that all my radii have a length of 8. And I also know the distance from D to B is 25, but I don't need that to solve for AB. So based on the theorem, if I have a tangent touching a circle at the edge, then I have a perpendicular point. So I'm going to use Pythagorean's theorem. And the arrow's facing a number. I'm not pointing it to the 9, I'm pointing it to segment CB. So using Pythagorean's theorem, my goal is to find a leg length, which is AB, so I'm going to do subtraction. Now the question is, what is the length of CB? Well, I know that CE plus EB equals CB, so CE is 8, EB is 9, so the length of CB is 17. So I'm going to do 17 squared minus 8 squared to get the length of AB. Hang on, I gotta use a calculator. I'm getting a length of 15, and that is the correct answer to this one. So hopefully you got it before I did. And maybe this is getting a little easier, I hope, and we'll go from there. Okay, looking at these next two examples, I've kept them together because we have a new theorem, and this theorem I feel like is easier than the first one. When I say that, it's just because the math seems a little bit easier to do. This theorem says if two segments from the same exterior point are tangent to the circle, then they are congruent. Keyword congruent. That's going to help us out with the math. So right now on the example 4, I'm looking at it and I don't see any radii in the circle, so I don't have anything to mark in red for me. But following the theorem, I do have 2 points of tangency meeting at the same exterior point, which is point P. And since they are congruent, it just says I have to set them equal to each other. So the question is, what number times 2 minus 3 gives me 27? So if I add 3 to both sides, I get 2x equals 30. So what number times 2 gives me 30? And that is 15, which is all they asked for. So you have solved for example 4. Looking at example 5, there is more written, and it just says find the indicated values. So I'm going to start with solving for x. I do know that if 2 points of tangent C meet at the same exterior point, they are congruent. So I'm going to do 2x minus 13 equals 48. And to solve for x, step 1 would be to add 13 to both sides. So that leaves me with, I believe, 61. So x is going to be a decimal, and that is okay for these for this topic. So we're putting x at 30.5. When we look at the measure of angle ABC, notice Ms. Clements didn't mark her radii first. And it did say in that first theorem that if there's a point of tangent C meeting the radius, then what happens? That's right, we have perpendicular angles. So just by remembering that theorem and marking my picture, I now know that the measure of angle ABC equals 90 degrees. And then we have to find the length of BC, which, hey, I marked it in red, so I know it's a radius. That means that I'm going to have to use Pythagorean's theorem. I know it says BC, but if you remember, all the ones in red have the same length. So I'm going to use Pythagorean's theorem, and I'm going to use this one on the bottom since I have 2 of the 3 numbers. I'm going to box this out of the way. Since they're giving me the hypotenuse, I'm going to do 52 squared, and I'm sorry the handwriting's sloppy, minus 48 squared. Take the square root of that in the calculator. And I'm getting an answer of 20, and I hope you did too. If not, then we will compare notes when I get back. But that is example 4 and 5 with a different theorem, but also implementing the first theorem that we talked about. So please take a moment to finish these notes or these examples and maybe go back and write some questions down for me, and we'll go from there. Okay, we're getting into some new terms, which they're not that bad. But this one just says when circles are inscribed in polygons, that means when circles are inside polygons, then the polygons themselves, triangles, rectangles, pentagons, are said to be circumscribed polygons. It doesn't change anything that you've learned thus far. So in such polygons, each side is tangent to the circle. I don't have any radii to mark in red, so triangle TRW is circumscribed about circle A, so there's points of tangency. If the perimeter of triangle TRW is 50, and the measure of TK is 3, and WM is 9.5, and I'm going to change this in color so you can see something in just a minute. then find the length of TR. Well, we just got through talking about a theorem that says if two points of tangency meet at the same exterior point, then the segments are congruent. So point T is exterior for point K and L being the points of tangency. So that means TL is 3. Going on the same theorem, point W is the exterior point for K and M. So this one's 9.5. So I'm going to use that given information, and I'm going to add those up. So 3 plus 3 plus 9.5. Sorry. Plus 9.5 equals, I gotta get my calculator. Gives me 25. Now that's for the 4 that we see. We have a total of a perimeter of 50. So what I'm going to do is take all of the perimeter and then take out what we have. That leaves us with 25. That means that LR and MR, they are not radii. I know I'm using red, but I changed colors. They are equal to 25. So if we're finding the length of TR, I've still got to find the length of LR to add to TL. So if I took 25 and divided it by 2, I'm left with 12.5. So that means the length of LR is 12.5. I'm not done answering the question, because remember, to get TR, it's TL plus LR equals TR. So that's 3 plus 12.5. So our answer to all of this work, is 15.5 or 15.5 units. It's not that bad, it just takes a little bit of work. Okay, this example should be really easy because all you gotta do is put some numbers in there and add them up, because it says it wants us to find the perimeter of the polygon, which is just like we got through talking in example 6, where when two tangents meet at the same point of exterior, they are congruent. So I know that this one's a 3, and you may want to change the colors up just to see. That's completely up to you. But I'm using my theorems. Okay, so our perimeter won't be just the numbers that I've written in colors, it's all the numbers combined. So I have 3 plus 3 plus 2 plus 2 plus 3 plus 3 plus 1 plus 1. Make sure that you're adding up enough numbers to match up the number of segments they've given us. So if I add all those numbers up in my head or on the calculator, so I'm getting 6, 8, 10, 13, 16, 17, I'm getting 18 units for the perimeter. Hopefully you did too, and this example was super easy for you to understand. But if not, please again write questions on the example and I'll answer them as soon as I can. Okay, for this last example, I know it looks like a lot, there is a lot, but please don't get discouraged, because it just takes taking it in parts to get the whole thing. So again, like Miss Clements does, she starts with marking any radii in red. So for this example, I do see, I'm going to say, well, no, I'm not going to say 4, because that extends out. I shouldn't do that. Okay, so I know that there's 3, and then the other one kind of extends out. We can use it if we need it. But it tells us that given OA is 12, so if the length of OA, I'm going to change colors. So if from here to here is 12, and then we know OB is 6, so I'm going to use that information. So the distance from O to B is 6. So everywhere I have a red, I have a 6. I think now you might see the importance of maybe marking your radii first, because now I know that OE is 6, and that means E to A is 6 because the distance of O to A is 12, and it may not look that way, but that's why I do the color coding. We also know that the measure of angle BAC, which again I'm fixing to mark the entire from here to here, is 60 degrees. If the whole thing is 60 degrees, then what can we conclude that, let's just say, this piece equals? Since it cut it in half, we can say that each angle is what? That's right. That's 30 degrees. And then the other part is 30 degrees. So now we have, and I bet you can guess, we have 30, 60, 90 triangles because we have points of tangency, and I know it's marking it up quite a bit. So I'm going to pull out triangle BOA so we can look at it separately. And you may want to too when it comes to test and everything. Okay, so we know that this part is 30 degrees. We have a 90-degree angle, so that leaves us with 60 degrees right here. I'm sorry, my handwriting's not great. Okay, in a 30, 60, 90, and if I'm going too fast, you know, you can pause this. This is going to be our x square roots of 3. This is going to be our x, and then that's going to be our 2x. So I'm going to start with this information. I do know that the distance from O to A is, I'll kind of move that to make it look separate, is 12. So 2 times x equals 12. So what does x equal? That's right, it equals 6. So everywhere we see an x, we can put a 6 there. So maybe I have enough information to answer everything. If not, we'll go back and see what we have. So the distance from O to C is 6, which is our radius, and you might even want to put radius. The distance from E to D, let's see, is 12 because I had marked my radii earlier, so that made it easier. The distance from A to B, and if I looked down at the bottom at my triangle, because I kind of pulled that out and worked with it, because again, if you plan it out, it kind of makes the answers go a little bit easier. The distance from A to B is 6 square roots of 3. That also makes AC 6 square roots of 3. The measure of angle BAO, which I've marked in orange, is 30 degrees. The measure of angle OCA, again I had already marked that on my picture as well, which is 90 degrees because it's tangent to the circle, which is perpendicular to the radius. The measure of angle AOC, let's go back to my picture, AOC, is similar, well it's congruent to the triangle BOA, so I know that angle AOC is 60 degrees. The measure of angle EOC is also 60 degrees, it's the same one. And then last but not least, the distance from E to A, we kind of talked about at the beginning of the example. We have a length of 6. So again, stop this problem where you need to, revisit it, put questions down if you need to. And I am so proud of y'all for continuing your efforts to learn while I'm not there and watch these videos. And I do hope they help. Again, my goal is to see y'all and visit with you tomorrow. Y'all have a great day.